Lab1 concept velocity. In today's video, I'll introduce the main concepts of the lab, the experiment, code, models, discussion questions, and I'll wrap up the video with a conclusion. The main purpose of the lab is to observe the motion of an object at concept velocity and compare the practical results to the theoretical values, which will be shown later in the code. Later, after the experiment, we will find that uniform motion occurs when there is concept velocity in a single direction, meaning there's no acceleration occurring. The fundamental physical principle that supports this statement is Newton's first law and the position time graph. Now, if we can look at the video, you can see that I'm riding a scooter at constant speed from one light pole to the other, which is a distance of about 12 meters. In this experiment, the scooter would be the system, and the universe around it is specifically the ground, and the atmosphere are the surroundings. The video began at 0 seconds, and the position vector was 0 in the x, y, and z component. And the initial velocity was 3.6 meters per second, and this was calculated by taking displacement and dividing it by change in time. And if we look at this top right corner, we can see the position time graph that was plotted through this video. Now, as mentioned before, the main principle present in the experiment is Newton's first law. An object at rest will stay at rest unless acted upon by a net force. Because the speed of the system is not changing, and thus the scooter is in uniform motion, the net forces acting on the scooter sum to 0. As shown in the position time graph on this page, the function has a constant slope because the position is changing at the same rate. Now, this is a link to my code if you want to see my code. But if you take a look at it right now, we can see that the program will be plotting the graph of position time and velocity time right here. And what I did change in this program was the velocity. I changed it to 3.6 meters per second because the scooter was moving in the positive x direction only. I also went ahead and changed the time to 3.267 seconds because that's how long my experiment ran. The net force in this case is 0 because Newton's first law says that if you remain in a constant motion, your net force is 0. And I also changed the velocity update equation and the position update equation. Basically, this velocity update equation says that the velocity should remain constant because the net force will be 0, so the velocity should not change. And the position update equation is taken relative to the velocity. So since the velocity is the same, we should see the position should be the same at every interval since the velocity is constant. If we run the program right now, we'll see that the position time graph is very similar to the one we saw before. The slope is rising. And if we look at the velocity time graph, it is constant, as it should be. Now, if we go ahead and look at the plot I made with the observed line and the predicted line, we can see that the slopes are slightly different due to error that might have occurred when tracking the position of the system manually. Now, if we analyze the velocity time graph, this difference becomes more noticeable because you can see that the top graph fluctuates a lot due to precision difficulties when using tracker program. Since I was at a difficult distance or at far distance, it was difficult to track the exact position. And as you can see by the code, the velocity is constant as it should be. So in practice, the true velocity was not perfect, but in theory, it should be consistent all the time. Now, what would happen if we were to flip the axis? As you can see in the old video, the axis was pointing in the positive x direction. So what should happen is the magnitude should remain the same because the speed remains the same, but the vector's direction should become negative, as you can see right here. So the magnitude is the same, but the direction is now negative. So how many forces are exactly acting on this system, the scooter, to make the net force 0? We can assume that gravity, friction, air resistance, and the scooter's motor are all acting on this whole experiment, but it's difficult to calculate all forces. And so in conclusion, we observe the motion of a constant velocity object, compare the practical results with theoretical results, and at constant velocity, the net forces applied to the object are 0, meaning 0 acceleration. Now, I want to address the potential errors that I mentioned before, but tracking will never be precise, especially if you're at further distance and you have to zoom in a lot to manually track an object's position over a period of time. And the scooter speed could have also been inconsistent, but I made sure to keep the experiment as great as possible.